Good morning, everyone. Hope you're well. My name is Brian O'Halloran, and as Gary has said, I'm a senior industrial analytics researcher at IMR. So today's talk, we're giving you a quick introduction to machine learning and we'll further discuss how machine learning can be used in manufacturing and how it's increasingly being used in the manufacturing context. So without much further ado, let's do a little quick introduction as to what machine learning actually is. And so let's try to frame this in terms of a concept where most of you have prior experience of, and that of course is data analytics. And data analytics is really the art of kind of turning data into information and then using that information as insight into our businesses. Fundamentally, we're answering human business questions with data and allowing us to make better decisions using that data. Now, data analytics is just really kind of looking at the past. It's descriptive. So if instead we're looking to get an idea of how things will evolve into the future, we need a different framework for that. And that's where predictive analytics comes in. And that's where, in particular, where machine learning comes into play. Machine learning itself really is broadly speaking, the use of mathematical models to make predictions. And machine learning itself is actually just a subset of artificial intelligence, as you see in the diagram on the right-hand side. AI by itself is the capability of a computer system to be able to mimic human cognitive functions, to be able to do things like learning and problem solving. Whereas machine learning, it's a process of using mathematical models of data to help a computer learn without direct instruction from the user. You can see in the intersection, you've come across the term data science, and data science really is the practice of using machine learning and AI in conjunction with things like visualizations and exploratory data analysis to be able to perform those necessary predictive tasks. So in terms of machine learning itself, there are two main categories of machine learning, supervised learning and unsupervised learning. So we'll do a quick kind of run through as to how each of those actually works. Supervised learning basically is where we take a machine learning model and we train it. So we train it using labeled data, which is a response, and that may be numerical. So if we're doing things like predicting a number, like temperature, for example, or something categorical, like a yes or no response. The machine learning model will then find that relationship between the features, so the individual features of each of the observations, and the response that we're trying to actually predict. And so if we have new data where we don't have a response, so it's something that's in the future perhaps, we can use this relationship between the features and the response to be able to predict a new response. So we can make predictions on new data for where the response is unknown. And the primary goal of supervised learning is to build a model that generalizes really well. So as we kind of vary around the training data, we can go along and actually predict accurately the future rather than the past. So just to give you a quick example. So imagine we're going to build a classifier to classify coins. And so the observations are coins in the big bag. So the features for our coins here are going to be the size of the coin and the mass of the coin. And the response that we're trying to predict towards is the type of coin. And this is obviously hand labeled by a human. So that might be a 50-cent piece, a euro coin, 20-cent piece, and so on. So we'll train the machine learning model then using our labeled data. And so the model learns the relationship between the features, in this case, the size and mass of the coins and the coin type. And then if we have new coins where the response is unknown, we will give the model a new coin, and it will, based upon its size and mass of that coin, it will predict the coin type automatically. Unsupervised learning is a little bit different. So there's no labels here. And what we're trying to do instead is we're trying to actually determine the internal structure within our data. So we're trying to find representations within our data. So we try to extract that structure from within our data sets and see and find that latent information. So an example, we might want to find if we have grocery store shoppers, to be able to segment them into different groups, into clusters, and we do so by the fact that those clusters have similar behaviors. So again, an example, type of customers at a bar. Our observations are each of our customers. The features here are what drinks they buy, the people they interact with, and so on. And the response, as we mentioned, there isn't one. Instead, what we're trying to do is we're trying to group them by what they do in terms of the similarities in their behaviors. Okay, with that in mind, let's have a look at how machine learning can be used in a manufacturing context. And there are various different problem types that we can apply these supervised and unsupervised learning problems to. So for example, example use case questions are things like, can we predict when machinery will fail? Or if machinery will actually fail. Or based upon the history of the equipment, what other types of hardware should we actually monitor? And also, could we, for example, detect whether anomalous manufacturing has occurred? So for those 4 questions, let's look at what the problem, how we will approach them. So for predicting whether machinery will fail, this is a supervised learning problem, and it's a regression problem because we're trying to predict a number over a continuous range. In terms of if machinery will fail, again, this is a supervised learning problem, but it's a classification problem because we're trying to predict whether or not it will actually fail or not. So it's a yes or no. It's a discrete set of answers. Based upon equipment's history, what other type of hardware should we monitor? Well, this is an unsupervised learning problem. It's a clustering problem because we're trying to group together hardware without knowing the groups in advance. So we have no labels. And then finally, can we detect when anomalous manufacturing has occurred? Again, this is going to be an unsupervised learning problem. It's anomaly detection. Why? Because we're trying to look for things which are outside some definition of normal. So in terms of actual of industrial use cases, the main ones are things like predictive maintenance, quality inspection, manufacturing process optimization, and supply chain optimization. And we'll look through a number of these of these top 10. Predictive maintenance is really a technique that we can use to track the performance of equipment during its normal operation. And when we do so, we can use this as baseline to be able to detect when possible defects occur and to be able to fix them before they result in some sort of failure. Fault detection is the other side of the coin, and it's used to monitor systems and detect when faults actually occur. So if a fault occurs in the system, it can be isolated and classified based upon the type of fault, the location, and the detection time as well. So the goal for these really is to detect faults and to predict when maintenance should actually be performed. And predictive maintenance and fault detection usually combines various sensor readings. Sometimes you have external data as well, and it uses those the information from those sensors to predict on thousands of logged events. For predictive maintenance, predicting the remaining useful life of an asset using supervised machine learning is probably the most common technique in predictive maintenance. And an example of that is given in the illustration on the right-hand side. You can see we're predicting that for that particular asset, the remaining useful lifetime is 9.5 days after the horizon. Determining faults, we use unsupervised learning for fault detection instead. So a couple of examples: Deutsche Bahn, the German railway operator, they use data from their railway switches to predict failures, and so this allows to decrease the number of unexpected delays at scale. Example number 2, Nissan, they run a AI predictive maintenance platform to do remaining useful lifetime predictions on thousands of assets. And the company, they claim that they have a downtime reduction of about 50% and a payback period for the project of less than 3 months. And amazing, Nissan are able to scale the solution from just having done this for just 20 critical assets to thousands without having to increase the workload of the on-site predictive maintenance team as well. In terms of work we do at IMR, so one project that we're involved in is a European funded project called iBecome, which is for a multi-featured, highly configurable virtual building management system, and something that can be deployed to any type of building, irrespective of their energy and equipment types. One of the contributions that IMR has provided to this is we are providing a fault detection framework to flag anomalous events using unsupervised learning for use within the iBecome solution. And an illustration of that in terms of time series is given there in the diagram. Another use case is quality inspection and assurance. And so automated optical inspection is where we take a camera and it autonomously scans the device for catastrophic failure or quality defects. And computer vision, which belongs to deep learning, which is a subset of machine learning, is a foundation of optical inspection. And once the images are recognized, we use supervised machine learning to classify the images into the failure classes, whether they fail or not. The main benefit, as you might imagine, is are things like cost reduction. The main beneficiaries of these are large manufacturing facilities where even a small reduction in scrap or test time can yield very large savings. Pharma packaging systems are based in the UK. They have a solution which they deploy to existing production. And using machine learning, they quickly realize the benefits, where they're able to, by 2/3, reduce the cost of inspection, and by 1/3 be able to reduce out the false positive rate in their fault detection. Another quality inspection aspect works in things like additive manufacturing. Of course, additive manufacturing uses computer-aided design or 3D object scanners to use hardware to deposit material layer upon layer into very precise geometric shapes. And as the name implies, it adds material to create an object. But due to the variability in the process, it can be really difficult to ensure that, without having to do a lot of significant after the event validation, that the part has been manufactured correctly. And it's even more difficult to do so if in terms of monitoring process drift during time as well. So as part of the EU DigiBrain program, IMR, we're involved in one of the deliverables for this. We used unsupervised learning, in this case anomaly detection, to monitor the additive manufacturing process and to track anomalous conditions within the 3D printer machine during part creation. And this allowed us to monitor conditions in part quality in real time, rather than having to do post-hoc analysis. So obviously it allows the users to take prompt action if anomalous behavior is actually detected. Another use case is supply chain optimization. So it allows you to do predictive inventory management, for a variety of things such as reducing inventory planning time, monitoring inventory costs, optimize repairs, and to be able to find optimal reorder points. And so for these stats, we use supervised learning techniques such as time series analysis, probabilistic modeling, and simulations. An example, Continental, the tire manufacturer, they use software, they've built some models to predict the optimal point for tire changes in their fleet. And the model predicts the overall running mileage and compares it to the baseline, and uses this to generate actions. And so by using this, Continental are able to reduce the stock of the tires and to reduce the overall cost by about 25%, and also with the added bonus of improving safety upon the road as well. So in summary, machine learning is increasingly being used in a range of manufacturing environments, and for a wide range of use cases, including, as I mentioned, predictive maintenance and fault detection, quality inspection, and supply chain optimization. Now, machine learning provides huge potential for manufacturing, and IMR can certainly help you along that adoption journey. If you'd like to find out more about ML, we do offer a one-day introduction to ML course, which is hosted by me. It's intended for anyone interested in understanding potentially using machine learning, and it covers the core machine learning concepts plus more state-of-the-art approaches, and we give you some practical code examples. And also it gives you advice on how to plan and evaluate a machine learning project, and we outline the pitfalls involved. And the target audience, we don't assume that you have any background into this, but instead you want to learn the language and tools of machine learning in the context of AI. And that's it from me. Thank you all very much. I'll talk to you later.